All right, so in this video, we're going to go over our Unit 2, which covers all about matter. But before we can talk about matter in any significant way, we need to talk about ways that we can describe matter. And for that, we need to understand units and measurements. So let's go ahead and start on this. So our first unit or section, units and measurements. The vocabulary that goes along with it is really just the units, both base units and derived units that we'll be covering here shortly. So make sure you get this list of base unit, second, meter, kilogram, Kelvin, derived unit, liter, and density. Make sure you save these in your notebook so we can check on those later. All right, but starting right away, for our measurements, it's really just a way of collecting information in a quantitative way, right? So quantitative properties, these are things that we can measure. We can assign a number to them. We can assign them a unit as well. And so these are ways that we can tell how much stuff we have when we're talking about matter, maybe talking about weight. We can also measure distances and lengths, the distance to travel. Also, if you're cooking or baking something, you want to know how long to cook it for. So, we also measure time. And all these measurements, they're very important for sharing information with others. Like I said, if you're following a recipe, you want to know how long to cook your food for. You don't want to undercook it and you get food poisoning, or you don't want to overcook it and burn your food, right? Now we have all these ways to tell approximate measurements, but the thing is that they're not consistent. They can be different all the time. So if I were to tell you that that the front door is about 10 steps from my desk, well, you know how much a step is, but your step length might be different from my step length. So it might take you 12 steps to get to the door. It might take you 8 steps to get to the door. So you can see that that's not very consistent. But a lot of times it doesn't seem like a big deal. But when we're talking about science, right, we talked about this in the last unit and the scientific method. Scientists need to be able to recreate and replicate results for certain scientific inquiries that we make. And so for scientists, it's very important to be consistent and exact in all our measurements. So for that, we have the SI system. So now the system that we use, that we are familiar with, is called the U.S. customary system. It borrows a lot of things from the imperial system that the British used, but it's not exactly the same. That's why we have a separate name for it. But you're familiar with this one. We use feet and inches for length. We use pounds and ounces for weight, right? And so you're familiar with all these conversions. There's 12 inches in 1 foot. There's 16 ounces in a pound, and there's 8 ounces in a cup. So now the other way to look at this is that the metric system. A lot of other countries use the metric system, and it uses different units for this as well. It uses meters for length, liters for volume, kilograms for mass, and seconds for time. And really, the beauty and what's so convenient about the metric system is that it is based on multiples of 10, so converting between different units is actually very easy. Where you have in the customary system, 1 foot, same as 12 inches. Well, I'm not really sure where these 1 to 12 conversions came from. But in the metric system, it's a lot more straightforward. It's all based on 10. So if you have 1 meter, you can also think of that same length as being 10 decimeters, or 100 centimeters, or 1,000 millimeters. So you see that it's a lot easier going from 1 to 10 to 100 than it is from going from 1 to 12, 1 to 16, 1 to 8. Doesn't really make sense to me. All right, so if you look at this example, I have just a simple water bottle, and if you want to know how much water you're getting for the money that you paid, you know that in this water bottle you would have 1 liter. So this would be the measure in the metric system, but with the U.S. customary units, it's 1.05 quarts. I appreciate the accuracy of saying 1.05, but is that really practical? It just seems kind of inconvenient. All right, and so going along that line, I said before that a lot of countries use the metric system, and not a whole lot use U.S. customary system. And so in this map, you can actually see all the countries that use our system, and there's just 3 countries on here. The only one that you'll recognize is the United States, but every other great country in this uses the metric system. So it's just kind of ridiculous how the entire world uses these units of measurements, and we don't. All right, and so now we keep talking about the metric system. You've heard of it before. You're familiar with it a little bit. but actually the metric system had slight differences going from country to country, and so scientists just said that that wasn't good enough. So a few years ago, a few decades ago, really, they updated the metric system and they called it the Système International d'Units. It's French. There was French scientists that decided to standardize it, but for us, we'll just know it as the SI system or the SI unit, and it's very similar to the metric system, but just know that this is the newest, betterest version. All right, so next up we have the base units. And so you should know that the base units are just the fundamental units that we use for measurements. Everything else, every other property that we can measure will be some variation of these base units. But the very basic units we use to describe events or matter, we use time, length, mass, and temperature. Now, time, you might be familiar with this one already, but the SI unit we use for time is seconds. The symbol for this is S, or sometimes when you write that with numbers, it can get confused with the number 5. So you can also use SEC as the symbol for seconds. Now, on a technical level, the way that our scientists decided the standard for seconds is that it is the frequency of the radiation given off by cesium-133 atom. Now, this probably doesn't mean a lot to you right now, and that's okay. This is a very technical and very difficult definition, and I don't really expect you to know this every time, but just this is something that I should bring up to you, that it is the technical definition of what a second is, even though you're already familiar more or less with how long a second is. All right, next we have length, and in SI, we don't use inches and feet or yards and miles to measure length, we use meters. The symbol we use for the meters is just lowercase m, so notice that it is lowercase. If you're using a capital M, it's not correct, and you shouldn't be doing that. And again, the very technical definition for the meter is the distance that light will travel in a vacuum in a very small fraction of a second. Again, very technical definition. Don't ask me why it's this amount. I wasn't at the meeting, so I wasn't part of this decision. Next up, we have the mass, and again, we're not using ounces and pounds. In the SI system, we're using kilograms. Now, if you ever wondered about this, a kilogram is about the size of a sack of flour they can get at the grocery store. So you can see all this powder stuff, it weighs exactly 1 kilogram. So now that's a very large amount, or it can be a lot of stuff that we use to measure. And a lot of the times it might just be wasteful to think of things in terms of kilograms. So a smaller unit we can use is also the gram. We can use that for masses that are much smaller than a kilogram without losing accuracy on that. Now, the symbol for the kilogram is kg, both of these lowercase, kg, and the symbol for the gram is simply just g. So that makes sense. The gram is just g, a kilogram is kg. So keep those two straight. And an interesting fact is that 1 liter of water, volume-wise, it has the mass of 1 kilogram. So you'll see that there's a lot of coincidences here with water, because we use water to base a lot of our measurements off. Next up, we have the temperature. And again, you probably already know temperature. You know that it's how hot something feels or how cold something feels. But the technical definition of it is not the feel of something, but it's a measure of the quantity of the average kinetic energy that particles have that make up an object. And what does all that mean? I know it's very technical, so let's pull up a simulation to see what we can talk about. So think of this as a chunk of matter, and we can see the individual particles that it's made of. Now, this simulation is paused, but once I play it, notice that the particles all start vibrating around. They're moving around a little bit, but they're not going anywhere. And this is what the particles of any piece of matter will do at the molecular level. They're always in constant motion, and that amount of motion, the amount of energy that they have, that's what we measure for temperature. So on the second simulation, you can see that I have all these different gas molecules in a container. and you can see them bouncing around, and they actually change their speed and their energy if I were to change the temperature. So if I dial that down and just press play on this, you can see that I have a very low reading on my thermometer, and that the particles are moving, at a pretty good pace, right? I can take this temperature slider and lower it, so you can see that at a lower temperature, these particles are moving a lot less. Or if I were to raise the temperature, again, they start moving faster and faster and faster. All right, so you can classify that as being faster, or you could say that all these particles have a lot more energy when they're moving around like this in such a fast way. You can lower the temperature, and you're essentially lowering the energy of all these different particles. Getting back to this. Now, the way that we measure temperature, we can use two scales, and they are the Celsius and the Kelvin scale. And this is what they both look like compared to each other, just relatively. Now, what a degree is just a small amount of energy. It's just a measure of an amount of energy that we can have. And what's interesting is that in the Celsius and the Kelvin scale, 1 degree represents the same amount of energy. But what's different is the range that these two scales are found in. So the way that the Celsius scale was established is that scientists took water. They were studying water, and so they cooled it to the point where it froze. They measured that temperature, and they set that as the standard. So the temperature that water freezes, that becomes our new 0 degrees Celsius. Then they did that same experiment. They measured the temperature at which water boiled, and they decided that was 100 because 100, it's a nice number to think about. And then that difference in temperature going from the temperature that water froze and the temperature that it started to boil, they decided to split that up into 100 equal segments. And so that's where we got our definition of the degree, how much energy it takes to raise water, to raise the energy of water. So now I think that's very useful. We base a lot of our systems based on water, but we know that we can get things a lot colder than the point that water freezes, right? And so the Kelvin takes that into account. And so actually where we measure our Kelvin scale, where we started, is called absolute zero. And that's the temperature at which there is no molecular motion for the particles of matter. So if we go back to this one, remember that I told you that these particles are always in constant motion. They always have some amount of energy. Well, if we were to just stop that altogether, if these particles were set in place and they did not move or vibrate in any way, then this would be absolute zero. Their energy, their temperature is absolute zero, and it cannot go any lower than this. You cannot get into a negative temperature with Kelvin because you can't have negative energy. All right, and so now we're done with all of our base units. So remember, the base units are the most basic type of information that we can get, the most basic type of observations that we can make. Now, these derived units will be using combinations of base units to tell some other type of information about an object or a piece of matter. Now, the two we'll be focusing on are volume and density. These are both derived units, so let's see why they're derived units. For volume, it's a measure of the three-dimensional space that an object takes up. So now you're familiar with an x and y axis from math or geometry. You know that things can take up space, going left to right and up and down. Those are your x and y axes. But in the real world, you know that everything's not flat. Everything's got a certain depth to it. And so that is the z-axis that you can think of as in and out of the page in this example. So if you look at this image, it looks very 3D. That's because we're shown both an x-axis, a y-axis, and a z-axis. Now, and the combination of all those three axes will give you a new measure that will be our volume. So because volume, we're taking three measurements of length and combining them into a single measure, it becomes a derived unit, even though we're just using our same unit of our base unit of length, which is the meter. And then finally, we have the density of an object, and the density refers to how much matter there is in a certain space, or the amount of matter per unit of volume. So if you look at this visual here, And these squares represent the same amount of space, and the green balls, these are our particles. You can see that in this same space, we have different numbers of particles. And if we start here with just 5 particles, we can say that we have a relatively low density. With 9 particles, it's a little bit more dense, and just the more green particles that we stuff into the same space, the more our density will rise up. The mathematical formula for density, we'll be working more with this later in the labs and in our future sections, but just keep in mind that this is the formula for density, that is just mass over volume. This means that you're going to take your measurement of mass of an object and you will divide it by the volume that you measure. Now we have the SI prefixes. So a lot of the times our base units, they might not be the most practical way to think of things. Sometimes they might be too big for any measurement we want to make, or they might be too small for any measurement that we have. So if you can think of it this way, if you wanted to measure the length of your pencil, well, a meter is way too big to say how long a pencil is. You'd be getting into a tiny fractions of a meter to describe your pencil. So in those cases, it would be more useful to use a ruler to describe your pencil. But now, a ruler doesn't tell you the whole size of a meter. It's just a smaller portion of that meter. And we can adjust our units without losing any accuracy, we can put them into a more useful range by using our SI prefixes. So you may have already seen these before, and there's a few more on this list than you're familiar with probably. And again, this is just a short list. There's a lot more prefixes that we use in science, but these are really the most common ones, the ones that I want you to be more familiar with. So you can see that we have giga here to represent the billion. Mega represents 1 million. Kilo will represent 1,000. Hecto is 100. Deca, 10. And then the base, we use that for just 1. Then we can get into decimal places. For deci, it is 1/10 of the base. Centi is 1/100th of the base. Milli would be 1,000th. And micro is 1/1,000,000th. All right. On this column here, we have the scientific notation. Don't worry about that just yet. In our future section, we'll be covering scientific notation, and that will make more sense whenever we get to it. So just keep in mind that for now, we're not doing anything with scientific notation, but we'll come back to it later. Now, the way we use these prefixes is that we just take the name of the prefix and you put it in front of the base unit that you're measuring. So, we talked about grams, but really we talked about grams, and you know that you have kilograms that you can measure. So kilo just means 1,000 and grams means grams. So with a kilogram, you have 1,000 grams. Another example is that say that you may have 100 meters. Well, remember that meter is your base, so that represents the 1. And if you wanted to convert it to another range of unit of measurement, you could call 100 meters. You can also call it 1 hectometer, because hecto represents 100. You can also have 100 meters, and that could also be used as 1,000 centimeters. That's 10,000 centimeters. And finally, 100 meters, you might also call it 0.1 kilometers. And so now these values, they all have the same value, even though you're using a different range of numbers. And so if these different values don't make sense to you just yet, just hang in there. In the next section, we'll be getting into the conversions for these SI prefixes, and it'll make a lot more sense once we get through that.